Alright, so in this video we're going to go over the concept of continuous functions. Alright, so conceptually, a continuous function is a function where if you were to draw it out, if you were to graph it, you never pick up your pencil as you're drawing that graph. So the graph is one continuous stroke. Right? So that's the conceptual definition. Well, mathematically, how do we prove that? Well, mathematically speaking, there are three requirements, or there are three conditions that must be met to say that a function is continuous at a particular value, x equals a. Okay, what are those three conditions? The first condition says that we must have a limit as x approaches a of f of x, it must exist. All right, so that's saying that our two-sided limit that we've spoken about in previous videos must exist. The second condition is that f of a must exist. And what that means is that we must have a closed dot. We must have a function value there at x equals a. And then lastly, the third condition of continuity of a continuous function is that we need that limit, that two-sided limit. The limit as x approaches a of f of x, we need that to be the exact same thing as f of a. That is the output value, the y value, so to speak, whenever x is equal to a. When all three of those conditions are met, we have what's called a continuous function. So what I want to do next is I want to kind of look at, I have three graphs here, A, B, and C. And I want us to go through each graph and I want us to determine why each of these graphs are discontinuous. Discontinuous means not continuous. And I want us to specify which one of those three conditions are violated in these graphs. So if we look at the graph from part A here, we look at from the graph from part A is that we notice that first of all, the limit as x approaches a of f of x must exist. Well, the limit as we approach from the left will be whatever that y value is there. And the limit as we approach from the right will be this particular value. So we know from previous lectures that if the left-hand limit differs from the right-hand limit, that means that the two-sided limit will not exist. So for graph A here, we can say that this function is not continuous because the limit as x approaches a of f of x, it doesn't exist. And remember, we write D N E whenever we talk about does not exist. Right? The limit does not exist because the left-hand limit is different than the right-hand limit. Now we have an f of a value. Here I'll highlight it. That closed dot there means we do have a function value x equals a, but since the limit does not exist, that function is not continuous. All right, let's keep it moving. Look at the second graph here, graph B. All right, as we look at this, we ask ourselves, first of all, does the limit as x approaches a of f of x, does that limit exist? Well, yes. The limit as we come from the left is going to give us whatever this value is here on the y-axis. And the limit as we approach from the right is also going to give us that same value. So the limit exists coming from both sides. So this limit does exist. All right, so we're good there. But what's the matter? What's wrong? Do we have an f of a? We do not have an f of a because we have an open dot at x equals a, but there's no closed dot to be found. That means that there's not a functional value, a y value there at x equals a. So because of that, we can state f of a does not exist. And because f of a does not exist, we can say that this function is not continuous. All right? Okay, let's move on to the third graph. The third graph here, let's see what we have here. Do we have a limit as x approaches a of f of x coming from both sides? Well, certainly similar to the graph B, when we approach that value of x equals a from both sides, we do agree on the same limit there. So the limit does exist as we approach from both sides. All right. Do we have an f of a? Does f of a exist? Yes, it does. And I'll try my best to highlight it here. F of a is that closed dot right there. So f of a exists. So we have met two of our three conditions. But what's that third condition? The third condition is that we need the limit to be the same thing as the f of a. And as we can see in this example here, they are not the same. So we have that the limit as x approaches a of f of x is not the same as f of a. Therefore, this function is not continuous. Okay? All right, so I hope that kind of clears up what the three conditions of continuity are and what it looks like whenever one or more of those are violated. Okay, next example. All right, so here we have a graph of f of x, and they want us to check the three conditions to determine if this graph f of x is continuous at x equals 4. Okay. We're clearly looking at it. If we were to draw this graph around x equals 4, we can see that, and when we get close to x equals 4, we have to pick up our pencil and draw the point down here, and then continue to pick up the pencil and draw it there, right? Because of that, we know it's not continuous, but let's go through the mathematical definition, and let's prove why it's not continuous. So the first condition, we need the limit as x approaches a of f of x to exist. Okay? Does it exist? Meaning, as we come from the left, do we get the same limit as we come from the right? Well, certainly, as we come from the left, we can see what the graph is trending towards. As we come from the right, we see what the graph is trending towards. And we can see that the left and the right-hand limits agree on what that limit should be. So because of that, the two-sided limit will exist. So yes, the limit as x approaches a of f of x, it exists. Secondly, does f of a exist? Right? Do we have a function value when x is equal to 4? Yes, we do. Even though we have an open dot on the main part of the graph, we have this closed dot down here that I've highlighted in yellow. Because of that, we can say, yes, f of a exists. But are we continuous? We are not, because what's the third condition? The third condition is the question of, does the limit as x approaches a of f of x, is it the same thing as f of a? And we can see that they're not, right? The limit for the graph at x equals 4 is up here, the open dot, whereas the actual function value is down below in that closed dot. So because of that, we can say the limit does not equal the function value f of a. Therefore, we can say this function is not continuous at x equals 4. Okay? So make sure when you're doing your homework that you understand why it's not continuous, because you will be asked to select that. All right. Next example. Okay, this next example, we have what's called a piecewise function. And piecewise gets its name from each piece of the graph is only valid for the particular domain that's given over on the right side. So for instance, for all x values less than a -1, this graph will look like the parabola negative x squared plus 5. At x equals 1, this graph will be just the constant value of 5. And then for all x values greater than 1, the graph is going to look like this parabola, the 2x squared plus 2x plus 5. Okay, I'm sure in previous courses you were asked to graph these. Right now, we're only going to consider, is this function continuous at x equals a -1? So to determine continuity, let's go through our definition. The first part of our definition says we need the limit, in this case, as x approaches -1, we need that, of f of x, we need that to exist. Okay? Well, to do that, we're going to have to check the limit as we come from the left and as we come from the right. And let's do that. Okay? And I'm going to do that in a different color here. So let's look at the limit as x approaches a -1 from the left of our function f of x. Okay? All right, so as we approach -1 from the left, I'm going to highlight here in yellow the part of the graph that we should pay attention to, right? So as we're approaching from the left, we're looking at values less than -1. That means we should look at this part, the -x² plus 5. Okay? And as we've talked about in a previous video, the domain here for x² plus 5 will be all real numbers. So we can just simply plug and chug to figure out that limit. What I mean by that is we can simply plug in -1 because -1 is within the domain of that x² plus 5, that -x² plus 5. So this limit will look like a negative of -1 squared plus 5. So all I did was I took my x value of -1 and I plugged it into my -x² plus 5. Okay, because there's no removable discontinuities there. All right, what does that give us? So a -1 squared is a positive 1 times negative is a -1 plus 5, which gives us a positive 4. So the limit as x approaches -1 from the left is a positive 4. Well, what about the limit as x approaches -1 from the right? Okay, the limit as x approaches a -1 from the right. Well, let's see. We're going to do the same thing here, very similar, but this time we're going to plug in our -1 into this portion down here, the 2x² plus 2x plus 5. Okay, let's do that carefully. So 2 times a -1 squared plus 2 times -1 plus 5. A -1 squared is a positive 1. Positive 1 times 2 is 2. Let's see here. 2 times a -1 is a -2. And then plus 5. 2 minus 2 plus 5 gives us, well, 5, right? 2 minus 2 is 0. 0 plus 5 is 5. Well, we can stop right there. We can stop right there. Because we have just shown that the limit as x approaches 1, a -1 from both sides of that function f of x does not exist. Why is that? It's because we came from the left, we got a limit of 4. We came from the right, we got a limit of 5. So right there we can stop and we say, okay, this limit does not exist. All right? So just peeking ahead a little bit, so what if that limit did exist? Well, the next thing that we would check is we need to check if f of a exists. Well, in this case, this will means f of -1. Okay? So what I mean here is, does f of -1 exist? And it does. They tell us that at x equals -1, we get a 5. So f of -1 equals 5. Okay? So that condition is satisfied. And then lastly, yet another reason why this is discontinuous is because we see that, well, excuse me, if you get to this point in the problem and you have a limit and you have an f of a value, right? Your third step would be to check to see if the limit as x approaches a of f of x, if your limit from part 1, if it equals your f of a. Okay? If this is true, then yes, you have a continuous function there. If it's not true, you do not have a continuous function. But once again, I want to be clear here. We stopped at step 1 because we found that our limit did not exist. So we are good to go right there. All right. Last example here. Okay, so we have yet another piecewise function. So given this piecewise function, find the value of k that would make the function continuous. All right, so once again, we're going to have to use our definition of continuous functions to determine a value of k that will make that function continuous. All right, so what's the first part of our definition? Is that we need the limit from the left and right sides to agree, right? Because we need the limit from both sides to exist. All right, so let's do that first. So we're going to look at the limit. All right, this is the first. Well, actually, we'll just do it this way. We have the limit as x approaches 2, right? because since the k minus 2x and negative x plus 4, those are linear functions, they're going to be continuous everywhere. The only part where this function could be discontinuous is going to be at that x equals a negative 2, right? So that's why I'm going to go ahead and base my limit off of approaching a negative 2. And I should make this a negative 2 here. All right. Okay, so let's approach the negative 2 from the left. Let's do that. So I know that looks weird, right? So it's a negative 2. Let's rewrite it. We're approaching a negative 2 from the left. So as we said before in the previous example, because it's a continuous function, at least the k minus 2x part is, we could just simply plug in chug, right? So we're going to do k minus 2 times and replace x with the negative 2. All right? So that's going to get us k plus 4. Okay? So that is the limit that's the left-handed limit for this function, for this piecewise function. Now let's do the same thing, except for let's approach negative 2 from the right. Okay? And so we're going to once again plug in negative 2, but this time we're going to plug it into the bottom part of the function because we're approaching from the right. So that would be a negative 2 plus 4. Excuse me. That should be a negative of a negative 2 because we are substituting in a negative 2. So we have a negative of a negative 2 plus 4. So that'll give us a positive 2 plus 4, which gives us 6. Okay? So in order for this limit to exist, we need the left-hand limit to be the same thing as the right-hand limit. So our next step is to set those two parts equal to each other and solve for k. So we'll take k plus 4, we'll set it equal to 6. Solving for k, we get that k is equal to 2. Okay? And so what does that mean? And that is actually our final answer. What does that mean? So k equals 2 is going to be our final answer here, but let's verify why that is the final answer. All right. So I'm going to substitute k equals 2 back into our function. So our piecewise function will be f of x equals, let me scroll up just a little bit. It's going to be 2 minus 2x for x is less than 2, right? All I did was plug in 2 for k, and a negative x plus 4 for x is greater than or equal to 2. All right? Well, let's check very quickly the three conditions to ensure why that k equals 2 is the correct answer. First condition, we need the limit as x approaches 2 from the left to be the same as the limit as x approaches 2 from the right. So let's double check that. So if I plug in, I'm sorry folks, that should be a negative 2. These should be negative 2s. If I plug in a negative 2 into the first part of the function here, it's going to be 2 times 2 minus 2 times a negative 2, which will be 2 plus 4, which we get is 6. And we saw that earlier, right? Now let's plug in, let's approach negative 2 from the right. And we will get a negative of a negative 2. Remember, plugging in negative 2 plus 4. A negative of a negative is a positive 2 plus 4. Once again, gets us 6. So what we see here is that the limit now, as x approaches negative 2 from both sides, it equals 6. So the limit exists. All right, the limit exists. Perfect. All right, our second condition. Our second condition is that we need f of negative 2 to exist. Okay? And it does. If you look at our function, I'm going to highlight it. For x greater than or equal to negative 2, we go along this bottom piece here, right? Well, all we have to do is plug in to figure out f of negative 2. All we have to do is plug in negative 2. So f of negative 2 will be equal to a negative of a negative 2 plus 4, right? Because it's negative x plus 4. And as we saw earlier, that equals 6. And so lastly, the third condition is that we need the limit as x approaches a negative 2 to be the same thing as f of negative 2. And that is the case because both of these parts equal 6. All right, so do you have to do all of that? No, but I wanted to prove to you why k equals 2 is the correct answer to make this piecewise function continuous. So all you have to do is to find your left-hand limit, find your left-hand limit, find your right-hand limit, and set those limits equal to each other and solve for k. That is going to automatically create a situation where you have all three conditions for a continuous function met. All right, I'm sorry if this video was rambling on, but I appreciate you guys watching it. I will see you in the next one.